right, so in this example, I've got propanoic acid in the beaker. So propanoic acid is HC3H5O2. Propanoic acid is in the beaker, and then to that beaker, I'm going to add sodium hydroxide. Okay, you're still going to, whatever you add to the beaker is still going to be strong. So either a strong acid or base, whichever one you're dealing with. In the beaker is what is the weak thing. So propanoic acid is a weak acid. I've got 20 milliliters of it, and the concentration is 0.5 molar. Okay, so right away when I'm going through these problems, these titration problems, is I want to look at what the millimoles are of the hydrogen ions that I have in the weak acid. Okay, so if I take 20 milliliters and multiply it by 0.5, 20 times 0.5 is 10. That's millimoles of hydrogen ions, okay, because I'm going to need that in order to figure out the problem. The setup is going to be the same. We're going to start the same as we did the other problems, like where you set up the BCA table and you figure out millimoles of everything you have to calculate the pH. So I'm going to start there. I've got 10 millimoles of hydrogen ions. Now I'm going to add 0.25 molar sodium hydroxide to that, and I want to figure out the pH after I add 15 milliliters, 40 milliliters, and 45 milliliters of sodium hydroxide. Okay, first of all, I'm going to go ahead and figure out millimoles of hydroxide ions for each one of these, just so I'll be able to use them later. So 15 milliliters times 0.25, which is my concentration of sodium hydroxide. That's 3.75 millimoles of hydroxide. So that's going to be used for part A. For part B, 40 times 0.25, that's 10 millimoles. That'll be used for part B. And then for part C, 45 times 0.25, and that is 11.25. Any questions on where I get these numbers from? It's the first step. If you can't do that, then you can't do the rest. All right, so then next, let's go ahead and do part A. Part A is to calculate the pH after adding 15 milliliters. Well, the first thing you've got to do is you have to figure out what the equation is that's happening in the beaker. So I have propanoic acid in the beaker, and when I add sodium hydroxide is a strong base, so it ionizes, splits up into sodium and hydroxide ions. The sodium ions don't affect the pH at all, so they're not part of the overall equation. They're not going to bond with anything or form anything new. So these are my two reactants that I have. So I have hydroxide ions being added to the propanoic acid. And those reactants, this hydrogen is going to come over here, it's going to form water. And then when that hydrogen leaves the propanoic acid, I'm left with just the propanoate ion. Okay, so that's my equation that I'm going to be working with, and it's going to be my starting equation for all parts, A, B, and C. What you're going to do is you're going to set up the BCA table, which remember is different than a ice table because it doesn't have concentrations. Ice tables have concentrations, and you try to figure out concentrations at equilibrium. The BCA table, you do millimoles or moles, and you just figure out how much you have left at the end. So in part A, well, in all parts, I start with 10 millimoles of the propanoic acid, 10 millimoles. This should say HC3H5O2. Okay, 10 millimoles of propanoic acid is what I'm starting with in the beaker. When I add 15 milliliters of sodium hydroxide, 15 times 0.25, I have 3.75 millimoles of hydroxide. What do I do next? What do I subtract from each of these numbers? 3.75, right? The 3.75 gets all the way used up, and I get 0 here. I subtract 3.75 and get 6.25 millimoles left right there. Water, it doesn't really matter. Over here, I start with 0. I add whatever I subtracted over on the reactant side. So I add 3.75 millimoles and get 3.75 millimoles as my product. the BCA table, this whole thing, it's kind of like a shortcut of doing stoichiometry, basically. Since everything here is a 1-to-1 ratio, it makes that easy to do. Once you do that whole table and you figure out what you have left after the reaction is complete, all the hydroxide has been used up, you're left with 6.25 millimoles of propanoic acid, and then you also have 3.75 millimoles of the propanoate ion, okay? So I'm just going to circle what I have left because it's going to help me figure out how to calculate the pH. What you should notice about what you have left is you have propanoic acid left. That's a weak acid. Hey.
I'm not sure if you sign that one.
Oh, yeah, cool. I will. There you go. And then over on the other side, the C3H5O2 is the propanoate ion. That is the conjugate base of propanoic acid. Now, when you have, this is an important thing, what I'm going to say next, okay? When you have a weak acid and its conjugate base partner, what have you created? Yes, you've made a buffer, okay? And the reason why that matters, that's the definition of what a buffer is, okay? So I know that, like, we talked about buffers already, and then, you know, we get to this point, and then people are always like, wait, what's a buffer again? Yeah, we know that buffer pHs don't change very easily. We showed that in the lab on Wednesday. But you should recognize when buffered solutions are made based on what you have left. If you have a weak acid and you have its conjugate base partner left at the end of that reaction, that's a buffered solution. Why do I care if that's a buffered solution? Because it's easier to calculate the pH of a buffered solution. Because we have that equation where I can just negative log the Ka value, which was given to me, 1.3 times 10 to the negative fifth, plus the log of the base over the acid. Which number goes on top? 3.75 or 6.25? 3.75. 6.25 goes on the bottom. And so you can calculate the pH that way without having to do any kind of ice table or anything like that. So when you calculate that, you get 4.66. For part A, we did before the equivalence point. So something for you, like a key idea, is that before the equivalence point on a weak acid titration, you're going to end up with a buffered solution. And so calculating the pH is just using this Henderson-Hasselbalch equation. Okay, any questions on that process? That's before the equivalence point. All right, next one. Part B is at the equivalence point. And, you know, when we did the strong acid, strong base titration, the equivalence point was the easiest one because everything completely neutralized out. Like you had the same amount of hydrogen ions and hydroxide ions, and they neutralized, they made water, and the pH was 7. But actually, when you're dealing with a weak acid titration, the equivalence point is the most annoying one to calculate the pH for. It's the most involved. So you have to start the same way. You have to start with your equation. You have to start with your millimoles of everything. So I'm going to go ahead and rewrite this equation. So hydroxide plus propanoic acid. You get water. You get propanoate. My millimoles of propanoic acid are the 10 millimoles that I got from the 20 times 0.5. And then I did 40 times 0.25 right here to give me the 10 millimoles. Okay? So you see that that's the equivalence point because by definition when you have the same number of moles of acid and base, that's the equivalence point. So you get minus 10 and 0, minus 10, 0. Over here, 0 plus 10. Okay, so I get 10 millimoles. Now, the reason why this is tricky is because the only thing you have left after this reaction, you don't have any weak acid left and you don't have any hydroxide ions left. All you have is this propanoate ion. What this propanoate ion does is this basically becomes one of those problems where it's like the ones where you dissolved a salt in the solution and you had a salt that had a negative ion that affected the pH. So is that going to make the solution basic or acidic? What? Basic. Okay, so I have to treat the rest of this problem like one of those salt pH problems. So what I'm going to do is I'm going to figure out what the concentration of this is first. So 10 millimoles divided by my total volume, which was 20 plus 40. I started with 20 of propanoic acid. I added 40 sodium hydroxide. Gives me 0.167 molar concentration of this ion. So your next step is to take that concentration and put it into an ice table. And so this equation actually like flips because now I have this ion in water and it's going to produce these as products. So your next step at the equivalence point is once you have figured out your concentration of the ion, then you have to make an ice table to figure out sulfur X, okay, the way that we've done lots of times. So I'm going to reverse this reaction. C3H5O2 plus HOH. Then I'll get the propanoic acid and I'll get hydroxide ions. Since you get hydroxide ions, that's why the solution is basic. So if I set up an ice table, my initial concentration of that propanoate ion is 0.167. This is 0 and 0. And then this is a regular ice table setup, so plus X. So I get X's over on the product side, and then minus X over here. So the question is asking me still to solve for the pH. So if I want to solve for the pH, I want to solve for X because then I can figure out the pOH and then I can figure out the pH from there. But what they give me in the problem is they give me the Ka value. Can I use the Ka value for this?
No.
No, it's so frustrating. So you've got to figure out Kb first because the solution is basic and not acidic. So when you do that, you get 7.69 times 10 to the negative 10th. That's X squared over 0.167. All right, you solve for X. It's the concentration of hydroxide ions. Okay, you get 1.13 times 10 to the negative 5th. Then you get the pOH by negative logging that number. It's 4.95. You subtract it, subtract it from 14, you get the pH. The pH is 9.05. Okay, that's a lot. That's the equivalence point when the moles are equal of acid and base. You start with your little stoichiometry table to figure out how many millimoles of product you have. You have to turn that into a concentration. Then you've got to reverse the reaction, make an ice table, solve for X, get a different K value, and then go from there. Any questions on that? Okay. This is probably the longest problem of the year. And then the last one, it gets easier, okay? That was the hardest part, is at the equivalence point. So this was at equivalence. Make sure that you're labeling this like A was before the equivalence point, B is at the equivalence point, because you're going to have, like on your test next Friday, you're going to have so many different problems. You're going to have buffer problems, you're going to have strong acid-base titrations, weak acid-base titrations, and every little section is just a tiny little bit different. And so if you just remember things like, okay, before the equivalence point is always going to be a buffer, then you go through that process. At the equivalence point, you always have to do 2 different tables, and then kind of remember the process. All right, so part C is asking me what is the pH after adding 45 milliliters. We'll do this one, and then we're going to stop for a minute, and I'll give you one to practice. Alright. Part C is after the equivalence point. Okay, so I'm going to go ahead and write out the reaction again. I get hydroxide ions plus the propanoic acid, and it leaves me with water and propanoate. Okay, my millimoles that I started with is always the same of the propanoic acid, 10 millimoles. The hydroxide ions, I found already what that number of millimoles was, 45 times 0.25. That's 11.25. So this goes here. Okay, take your smallest number. Oh, this is 0. So I subtract 10 over on the left side. I'm left with 1.25. I add 10 over here. Okay, so after this reaction happens, now what I have is I have hydroxide ions and I have propanoate ions. Both ions are basic. Which one of them is the stronger base, hydroxide or propanoate? Hydroxide. Hydroxide is always a strong base, okay? Propanoate ions, it's a conjugate base, it's weak, okay? So in this particular question, it's however much you have left of hydroxide that matters, and that affects the pH. So the strong base wins. It's kind of one of those types of questions. So then you just have to take your number of millimoles of base, 1.25 millimoles, and if you divide that by the total volume of the solution, so I started with 20 milliliters and I added 45 milliliters, that's going to give me, you get 0.019 molar. That's the hydroxide ion concentration. Okay, which you can negative log, get the pOH, subtract from 14, and get the pH. The pH is 12.28. Okay, one thing that I forgot to point out is that here at the equivalence point, it's important for you to recognize that at the equivalence point, the pH isn't 7 here. Because a lot of times, like in all of our stuff that we've done with acids and bases, like last year and earlier in the year this year, it was always when you neutralize an acid and a base that the pH was 7. But when you're dealing with weak acids, that's not the case. The pH at the equivalence point is the basic pH.